Okay, so I'm assuming that everyone can see me right now. So my name is Fraser Cain, and I am the publisher of Universe Today. And I've got with me Nancy Atkinson, who is the senior editor at Universe Today. We've got Dr. Phil Plait from Bad Astronomy, and we've got Alan Boyle from MSNBC. These are some of my astronomy science friends, and we thought we would have a quick discussion to talk about the recent discovery of Earth-sized planets around the sort of discovered by Kepler. So why don't we sort of kick it to Phil, and Phil, maybe you can sort of give people an overview of what was announced today, and then we'll sort of dig into the details. Now, if anyone wants to, you can ask some questions. If you post comments on the where we've got the Google Plus Hangout, I guess if you click the window, there's going to be comments popping down below that, and if you ask a question in those comments, then we'll see them, and then when we get a chance, we'll start answering some of those questions once we've run out of my questions. So let's get rolling. So Phil, what was announced today?
Okay, what was announced was the discovery of 2 new planets, actually in total 5 new planets, around a star 950 light years away. The importance of this particular discovery is that 2 of these planets are roughly the size of the Earth. This discovery was made by an observatory in space called Kepler. And what Kepler does is it stares at one spot in the sky all the time. There are about 100,000 stars that it's looking at. And, oh, you know what I should do? Aha, oop, lost my earpiece, but that's okay. Imagine this is a star and this is a planet. When a planet passes between us and the star, it blocks the starlight a little bit. And you see a dip in that starlight. And that's what Kepler is measuring. And it turns out the bigger the planet, the bigger the dip in the starlight. So you can actually just sit there, stare at stars, and see if they have planets, find out the period of these planets, because how quickly the starlight dips tells you how quickly the planet's moving around the star. And by the amount of the starlight blocked, you can discover how big these planets are. Now, using this method, looking at this one star 950 light years away, they found that this star is being orbited by 5 planets, 3 of which are much larger than the Earth, but 2 of which are actually very close to the size of the Earth. These are the 2 smallest exoplanets, as they're called, ever discovered orbiting another star that's like the Sun. Now, even though they're both about the size of the Earth, all 5 of these planets are actually orbiting very close to their stars. So the 2 planets we're concerned about, which are called Kepler 20e and Kepler 20f, Kepler 20 is the name of the star, and the planets are B, C, D, E, and F. E and F are actually still orbiting their star closer than Mercury orbits the Sun. So these planets are extremely hot. But the important thing here is that Kepler has discovered these planets. They're about the Earth. They are the smallest ones ever seen, and that makes us even more confident that if there are planets the size of the Earth orbiting a sun-like star at that magic distance where liquid water can exist on the surface of that planet, we'll be able to find them. Now I'm going to put my earpiece back in.
I could have been asking a whole bunch of questions to interrupt you there. No, that's probably the best way to go about it.
I don't like to be interrupted.
So I think that we should probably get rid of the big question that everyone's going to be asking right away, and I'll let Nancy crack that one, which is, does this mean that this is another Earth, that they found life?
No, definitely it's way too hot for life as we know it to exist. They're way too close, way too hot. But they are rocky worlds, the two worlds. It's really an unusual system. It's like nothing I don't think that any astronomers have seen before. There's the alternating Neptune-like worlds with the 2 rocky planets, so 5 planets total. None of them are expected to be habitable just because they're in way too close and way too hot. It would be way too hot on those planets for life as we know it to exist. Now, other life, the jury's still out. We don't know about that. But definitely an interesting system. And I did ask the scientists about the dynamics of how a system like that could work, where the rocky planets and gas giants are kind of intermixed, because, clearly it's not like what our solar system is like, where we've got the kind of the delineation of the 2 kinds of planets. And basically they said they thought that the Neptune planets probably formed farther out from the star and then migrated in towards the star, and somehow the planets just got kind of jumbled together.
So, Alan, maybe you can give us some perspective then. How does this discovery relate to the recent, like the Kepler 22b discovery, which was the planet in the habitable zone?
Well, we're seeing all sorts of planets that have some of the characteristics of what is the gold standard, an Earth-like planet in an Earth-like orbit around a Sun-like star. And so the earlier planet was more like Neptune when you talk about size, and so that's not quite right. These planets are, the size is right, but they're too close, they're too hot. And so what Kepler is doing over the next couple of years is to continue to stare at these planets, as Phil said, and it'll take about 3 years to really try to confirm that sort of Earth-like planet in an Earth-like orbit. And it's going to be really tough, because one of the things that they do to confirm that they're really looking at a planet is to take other methods, a method that's called the Doppler method, where they look at the gravitational effect of a planet on its parent star. How is the star moving around because of that gravitational effect? It's easy to do that when you have a big planet that's close in. Not very easy when you've got a small planet that is far out as Earth. And so I think that's going to be the key issue, is that we've got all these candidates that could be Earth-like, Earth-sized planets, but how do you confirm that what they're looking at is a real effect? I think that's going to be really challenging. They have other ways to do it. There's one type of technique they call transit timing, where they look at the precise timing of how these planets, or whatever they are, go around the star, and they work it out mathematically so that they can figure out the masses of the planets. But it's going to be more and more difficult to really focus in on those alien Earths that everyone is looking for.
And I guess that's the big question, right, is we've got half of the puzzle. We've got a planet that's a huge amount of mass in the habitable zone, which is Kepler 22b, and then now we've got these planets which are Earth-sized, but I think, as Nancy said, Mercury, hell worlds. So not the kind of place the lava planets that you'd want to live, but you've got the right amount of mass. And so obviously the dream here, the hope, is that you're going to get those two discoveries coming together. You're going to get Earth-sized worlds located within the habitable zone of the parent star, and that is not what's been discovered yet so far.
Right.
Phil, question for you, Phil. How do you feel about sort of this discovery and sort of what's going to come next then?
Well, it's one step at a time, right? It's like you said, we have sort of one from column A and one from column B. We have a planet in the right place but the wrong mass. Now we have planets that may have the right mass but they're in the wrong place. What we need, as Alan was saying, was these two things together. It is tough. You can imagine that the bigger the planet, the more it blocks the star's light. So the smaller the planet, the less light it blocks. If you have a little tiny planet passing between us and the star, that starlight only drops a little bit. That can be really hard to detect. Stars aren't just steady sources of light. They change their brightness. There may be stuff between us and them, dust or whatever. There's also sunspots. There are other features on the surface of stars that can change their brightness. And all of these can sort of mimic what a planet looks like. And our goal is to find a star that's like the Sun and a planet that's like the Earth, which means that if the star's a little cooler, the planet's a little closer in. If the star's a little hotter, the planet's farther out. But either way, that planet has to pass directly between us and its star. That transit, as it's called, doesn't last very long, and then you have to wait until it does it again. Now, for the Earth, that would take a year. It would take 365 days to see that repeating pattern. Kepler launched in, I think, March of 2009, so it's only been about 2.5 years. Even if the day after it launched, they were looking at a star and saw a planet transiting, it would be a year later, 2010, before it happened again. You'd have to wait another year, 2011, before it happened a third time. So we're right now basically in that time frame where we'll start to see planets like this, where they transit on the period of roughly a year. And that transit's very small. So if you find one, how do you know it's real? The astronomers were careful to say in this release today that these two planets that are orbiting the star, they're the size of the Earth, are still too low mass to actually detect how they're tugging on the star. So they're only detected using this transit method. The other 3 planets were massive enough that their gravity could tug on the star enough that as they orbit the star makes a little circle like this. So as they're going around, it's doing this, and we can detect that. But the other planets are just too low mass to do that. And if a planet's farther out, that makes it that much harder to detect. So as Alan said, this is going to be really tricky to do. I think it's possible. I think Kepler was designed to do this, to find these guys. Confirming it is going to be a real problem. I bet sitting in the database right now of Kepler, there are planets like the Earth on Earth-like orbits around sun-like stars. They're
Absolutely.
there.
Yeah.
The problem
Really?
is going to be teasing them out of the data. Oh, I'm quite sure they're there.
Well, I mean, that was really interesting what you
I'm
said.
guessing though.
Right. I mean, in the announcement today, when we listened to the teleconference, we read the press release. They went way out of their way to say, by the way, we have confirmed the discovery made by Kepler using these other methods for some of the planets, as you said. So you've got that both the discovery by Kepler, which does the transiting method, but also confirming it with the gravitational tug back and forth. I mean, that is the most solid evidence you can possibly do. It wouldn't have announced this in any other way if they didn't have such a solid form of data. And so you can see, I'll bet you, I mean, I wish we could sort of, ask them, on the side, not on the record, what have you got in that database that you've already discovered? And I think you're right. There are going to be those planets. There are going to be planets on sun-like stars, in Earth-like orbits, in the habitable zone, and they're just waiting for ways to confirm it, which unfortunately, with that size of planets, there's no easy way to confirm them because they're so low mass. We need something like the terrestrial planet finder or something like that out there.
Go ahead, Nancy.
Go ahead, Nancy.
Well, it was interesting to note they talked about some new software that they have developed called Blender, and I'm assuming it means blending of all the properties that are needed to find the kind of holy grail of exoplanet that we're all looking for. They didn't go into much detail about the software. It would be interesting to find more about it. Again, it's called Blender, if anybody knows more about it.
No, I haven't heard of that. That's interesting.
And was that software used to confirm the discovery, or software used to tease the data out of the Kepler stuff? They
used it to confirm the discovery, and they're really, really confident that the 2 planets that they announced today, Kepler 20e and F, that they really are planets and not something that's kind of mimicking an exoplanet in the data.
Yeah. Now, mind you,
that software.
Mind you, when you're looking for a planet like Earth, and I said it only transits once per year, these planets are so close into the star that their orbital periods are a matter of days, not months. So when you're looking at this one star for 2.5 years, like Kepler has been, they have many, many, many transits, and you can measure the timing between the transits and say, oh yeah, you know what, every 6 point whatever days we're seeing this one transit over and over and over and over again. We can be pretty sure that's a planet. They did this, and that's how they can confirm that there were 5 planets there. There are 5 separate transits. Then they looked at it with a ground-based telescope that looked for the Doppler shift, and they were able to see 3 of these planets, and the tugging on the star matched 3 of those cycles. The 2 they couldn't find were these 2 smaller planets. But the fact that they're so close in and we saw so many transits means that you can be very, very confident that those planets exist.
So I'm not sure if this worked for people, but I've shared a screen of the various planets. You can see the planets that have been discovered, and they're compared to the Earth and I think Venus there. So you can sort of get a sense of the size. I mean, that's really exciting. That's amazing.
Yeah, this is an artist's conception, by the way, just to make sure.
Yes.
This is, and I get that question all the time, right? We're not directly seeing these planets. These planets are 1,000 light years away. They're incredibly faint, but we're just seeing them indirectly by their effect on the star. So by knowing how big they are, looking at the transits and all that, they can make an artist's conception of what they look like. And that's where this came from.
That must be a fun job, to be the artist, to just create planets from scratch. But there have been some planets that have been directly imaged, although there's always a debate among astronomers about whether what you're really seeing is a planet. But that's using a different technique, direct observation, and they hope to do that someday. For now, we've got the art.
The two things to say about that is actually our computer modeling of the physics of these planets is getting good enough that even though we don't know exactly what these planets look like, we can kind of have, we can guess about a lot of this stuff. And we are detecting atmospheres around some of these planets. So one of the very first transiting planets ever seen, which is much larger than, much more massive than Jupiter, is actually bleeding away its atmosphere. It's so close to the star that its atmosphere is like a comet getting blown off the planet. We could detect that. And some of these things, if they're very close in, we know that they're rotating at this. They're spinning basically at the same rate they're going around the star. It's the way that gravity works out. And so we know that one face of the planet's always facing the star, and you can model if this planet has an atmosphere, what does that do? How does that circulate heat? How do things flow around? With Kepler, with planets that actually aren't exactly edge-on, their orbits aren't precisely aligned, and so that we can, when it goes in front of the star, we can actually see it as it goes behind the star as well. You can actually see how the planet reflects the starlight. It's kind of like looking at the phases of the moon, and you can actually see, here's this planet going around this other star. We can see how the star is heating it, and that tells us about the atmosphere as well. There are a lot of little hints going on here. And as Alan said, we do have direct images of some planets that we know are of planetary mass. When you start dumping a lot of mass into a planet, it starts to look an awful lot like a star, and it can be very difficult to tell the difference, especially when they're very young and they've got a lot of heat left over from when they formed. So there's some arguments about some of these direct images of, you see a star and a planet seen by a telescope, but there are other ones where we're quite sure that these things are low enough mass to be planets. And we've seen a half dozen, like 7 or 8 or 9, something like that. We have direct images of these planets. It's phenomenal.
Yeah, we're at the point now where we're actually, I've got a cool sort of screensaver going on of all of the images related to the discovery. So instead of me talking, you can see images from the thing. But yeah, we're now, this is going to explode. We're now going to get thousands of planets. We're only like 12 years into this, right? From discovering the first planet with the gravitational method. Now we're looking at, bordering on thousands of planets. This is just going to explode now, thanks to Kepler and some of the other missions coming out. So I thought we would sort of switch over to questions in a second now. But before we do, perhaps the takeaway. What's the thing that you end up at a cocktail party and someone says, "Oh, did you hear that they discovered planets?" Or I know you like space. What's this planets thing? What's the advice that what's the nice elevator speech that we can give people so they can walk away and both spread science and have less misinformation passing along? Alan, why don't you give us your what would be the takeaway?
Well, I'm a big Game of Thrones fan, and so one of the things that they always say is winter is coming. In this case, it's like a springtime for planets is coming, that these are the harbingers of these alien Earths that everyone's been talking about in science fiction for decades. So the springtime for the planet search is coming. These are the first crocuses coming up.
That's cool. Phil, have you got a takeaway to
Well,
both boost science?
For a lot of these planets, winter is never coming because they're so close to their stars. When you're walking around and there's a pool of molten tin in front of you, it's like, oh, it's winter. It's finally cooling off. Yeah. This is amazing. The first planets we've been searching for planets for decades and decades. The first ones were seen in the early 1990s, orbiting these bizarre neutron stars. Then in 1995, the first planet was seen orbiting another sun-like star for the first time. There's a lot of controversy. Is this a real detection? After about a year or so, it was, it's confirmed. And the numbers have been growing essentially exponentially since then, especially with the launch of Kepler. We now have 4 or 5 different ways of finding them. There's this transit method. There's looking at stars and looking at them as they're getting Doppler shifted a little bit. For some planets, we're seeing them through what's called gravitational microlensing. I won't go into that. But there's all these different techniques, and we're finding more and more and more of these. I'm not saying it's getting easier, but we're getting better at doing it. And in fact, for some of these planets, they're orbiting stars that are close enough that you can look up and see these stars. They're naked eye stars. And with a small telescope and a nice digital detector, you could go out and literally into your backyard and over the course of an evening detect one of these transits. It's not that hard to do. So literally anybody can do this now. You can actually detect a planet orbiting at a star. And what we're finding in these numbers is that maybe not the majority of stars, but a huge fraction of them have planets, whether these are giant planets or little ones or whatever. Some fraction of those are going to have planets like the Earth. Some fraction of those are going to have planets orbiting their star in the habitable zone. And so we are just now taking off seeing these things. We still haven't seen that magic thing yet. It's coming. Those planets are, I can't say this for a scientific fact because we haven't seen it yet, but the statistics are so overwhelming. It seems like a rock-solid certainty that we are years away at most from detecting another Earth-like planet around a Sun-like star. I would bet on it. I can't publish that, but that's the way the wind is blowing.
But somebody somewhere at NASA is nodding sagely, I think, at this point.
That data could already be sitting on somebody's computer, and they're just waiting to confirm it. That is absolutely possible. I don't know.
Yeah,
it's possible.
Nancy, got a takeaway for us?
Well, my takeaway to follow on to what Phil said was, contact your Congress people about funding NASA, because Nick Gautier, one of the Kepler scientists, said in the news conference today that possibly a year or two until we do find the Holy Grail, the Earth-like planet. But to ensure that we do make that discovery and that we can find more, they need to extend the Kepler mission. And to do that, NASA needs more money. So, again, my elevator speech would be contact your Congress people and get them to fund NASA.
Yeah, I think for me, it's once that happens, everyone's going to want more information about, that Earth-like planet, and the tools will not be available. But the tool, the terrestrial planet finder, was designed, and the mission went a long way and then got canceled, and that tool unfortunately will not be ready to go and has been canceled. And so I think there's going to be a big outcry when that Earth-like planet does get discovered. People are going to be like, where's the tool to now confirm, let's see the life, and it'll be, sorry, we canceled that. You canceled what? So I think that, I hope that will put pressure to start the terrestrial planet finder back up again. So, all right.
Fraser, I just wanted to add a couple more things. One is that the Kepler mission right now is scheduled to close up shop in November, but they hope that they can get $20 million a year to keep it going a little bit longer. And then we also should mention planethunters.org. That's a project that some folks at Yale have put together to look through the data, and it's kind of like SETI at home, but in this case you're looking for extrasolar planets. And so anyone who's interested in it would probably want to check out planethunters.org.
That's perfect. All right, so and so once again, if you've just joined halfway, my name is Fraser Cain. I'm the publisher of Universe Today. I've got Nancy Atkinson, who is the senior editor for Universe Today. We've got Dr. Phil Plait, the Bad Astronomer, and Alan Boyle from MSNBC, and we're talking about this new planet discovery. And now we wanted to move into questions, and I hope that everybody has been posting their questions into the right thread. I'm only looking at a couple of them, I think, but I see one that has 80 comments, so I believe that's the one. So I'm just going to go through it and start throwing some questions at you. So first one comes from Steve Rem, who said that the planets are 950 light years away, so it's going to be literally impossible to ever get there. So how close do you think planets will be to be realistically possible for us to get there? I'll round robin this, so why don't you take this one, Alan?
Well, even at 4 light years or so, the Alpha Centauri system is probably not going to be visited anytime soon. They will be targets for SETI searches, and so if you're talking about communicating with intelligent life, that's the way you might want to do it. But it really just helps us answer the question of, were the conditions that were conducive to life rare in the universe, or are they more prevalent? And everything that we're seeing so far indicates that they're more prevalent than people might have thought some years ago. So it's not as if we're going to be able to colonize Kepler 20 anytime soon, but But who knows? Maybe if we get that faster than light travel thing going, we're there.
Right. Right. It would take lifetimes, hundreds of thousands of years for current spacecraft to make it. So as you said, it's just impossible. Right. So someone wanted to know. Let's see. Where was it? So someone asked, is there an atmosphere? Ken Morrison asked, is there an atmosphere, or is it like Mercury without an atmosphere? Nancy, do you want to tackle that one?
Yeah, basically the scientists said today it would be a Mercury-like planet, both of them, because they are that close into the star, and definitely not habitable at all, at least by our standards. So yeah, it's no atmosphere. It'd be very unlikely to have an atmosphere.
And just to follow on, Jazz Eminger asked, why is it too hot? Could there be life in thermal vents? So Nancy, do you want to just sort of tackle that one, and then I got one for Phil.
That's a good question. That's all I can say on that one.
Well, that sounds like you know more than you're saying, but you don't know more than you're saying.
No.
No. Okay. Good.
What they do is that they model what the radiance of the star is and how close it is, and they figure out what the surface temperature is just based on the physics of the system. And in these cases, they think it's too hot for liquid water to exist, so no hydrothermal vents, I'm afraid.
Right. If we discovered life on Mercury, then that might cause people to go back and think about it again. But right now, no. Okay, so Phil, the MAVEN mission, I guess a spacecraft is asking you a question. The odd configuration of this system, big, little, big, little, big, would you guess this is more of a factor of planetary formation or migration?
Well, I would say it's probably going to be both. We don't know. In our solar system, we have sort of the small planets huddling in close to the Sun from Mercury out to Mars, and then they get big, Jupiter, Saturn, Uranus. So it seems that there's a sort of a cosmic segregation going on. We do know, or we're at least very, very sure, that the planets in our solar system probably didn't start out the way they are now. Maybe the order was the same, but some planets were closer in, some were farther out. It's entirely possible that Uranus and Neptune literally swap positions at some point in the past. We're pretty sure things like this can happen as the planets move around. Their gravity affects each other and that sort of thing. In fact, when these first planets were found around our stars, they were these gigantically massive planets, much larger than Jupiter, much closer into their stars than Mercury. And it turns out it's hard to form a planet that massive, that close into the star. So what we think happens is they form in a swirling disk of material around the star, and as they pass through this disk, the way gravity and friction and other forces work, they wind up moving in closer and closer to their star. So planets can migrate into the star, and of course if you have a little planet orbiting and this gigantic planet moving in, that little planet's going to get in some trouble. It could get dropped into the star, blown out of the system, or get wiped out way out into the outer solar system. So we know that these planets form in one place and then over time move around. And our solar system is nice and neatly ordered. This one is exactly the opposite. When I first read it, I was thinking, oh, it's boy girl, but it's because that's when I was a kid, that's how we used to be fair. But it's big planet, little planet, big planet, little planet, big. Did they form that way? Maybe. It seems likely that there was probably some migration going on because they are so close to the star. They all probably formed farther out and moved in. When you model these sorts of things, it turns out all kinds of crazy things can happen. So this doesn't shock me. I think it's interesting, but it's not something so crazy that you'd have to think, oh, that must be wrong. So probably that's what's going on. It's a little bit of the way they formed and then what happened after.
Right. So if people have noticed a new person has joined us. This is Emily Lakdawalla from the Planetary Society, who has been wrestling with technology.
No, we can discover hundreds of exoplanets, but we can't get Google to connect to my computers. But we've solved it now, thanks very much to a commenter who told me exactly how to fix it. Social networking is awesome. Yeah.
Welcome to the future. We are blazing a trail with wrecked technology as we make our way through this. So the fact that this is even happening is pretty exciting. And so, Emily, I'm going to give you a question. You've missed the part where we all get to explain everything, but your question is it just lucky that the planets have been discovered in a plane between us and their star, or is there a reason for that? Or I guess the question is it blind luck, or are all planets orbiting between us and their star?
Oh, well, it's lucky that we see this particular system edge on, but of course the systems are randomly oriented in space. Some of them will be seeing them face on, like the Uranus system, where its moons are orbiting around its planet, and we never see them eclipse the planet. Some of them are more like Jupiter to us, where we regularly see their moons orbiting across the planet. And the same is true for all of these exoplanetary systems, where some stars, we're unfortunate, we are probably looking at them pole on, and we will never see their planets cross across their faces. But for fortunately enough stars, we're able to see those systems edge on and see many of these planets crossing their disks. And of course, most planetary systems, we think that most planetary systems have most of the planets orbiting in the same plane. And so that means that if we can see one planet in these systems, odds are good that we'll be able to see most of the rest of the planets that are orbiting that particular star.
Cool. All right. Alan, do we have any information on how old this star is, and does that have an impact?
I was just trying to find that out, and I think actually Phil may have some information on that, but I think I saw that it was twice the age of our star.
And, in the press conference, I was listening to it. I wasn't actually participating. One of the astronomers did mention that the system was billions of years old, but I didn't hear an exact number. And it's funny, these stars, many of these stars are so faint. A sun-like star at 1,000 light years away is pretty faint. Even from a few light years away, what is it, like 40 light years away, the sun is invisible to the naked eye. And we're talking about something that's 20 or more times farther away than that. So this is a very faint star, so it doesn't have an actual name, and that makes it hard to look it up in the database. And I don't think, Emily, I don't know if you know this, or anybody else online here knows this. If the Kepler database of stars like this actually exists, I found one for Kepler 10b, which was the sort of super Earth planet orbiting in the habitable zone. But it's hard to find all of these new planets all over the place. They're coming in so fast. It's hard to keep up with them.
Yeah.
If I can jump in, I think one thing to keep in mind is that although our sun is often described as a mid-sized star, it's actually larger than average. The vast majority of stars are red dwarfs or smaller. And so odds are good, again, that most planets are orbiting stars that are cooler than ours, so they can be much closer to their stars and still be in the so-called habitable zone.
So I guess, well then, since Phil jumped in and answered Alan's question, I'm going to throw Alan this next one then. Richard, you're going to keep getting questions.
Handed it off to me. Come on.
I know. He can't pass.
I think Emily knows the answer to this one.
No. So Richard Wright. No, you'll like this one. It'll be fine. It'll be nice. This is a softball. So Richard Wright asks, is there really zero correlation between the galactic plane and star system planes? That seems counterintuitive. And I guess I can see what he's asking. He's saying, like, here in the solar system, we've got the sun, we've got the planets all in the same plane, and then the moons orbiting the planets all on that same plane as well. So could you take that model to the next level? You've got the Milky Way, you've got the stars going around the Milky Way. Wouldn't you have the planets orbiting in that same plane?
I think that there would be something of a correlation. I mean, it wouldn't be, statistically speaking, you would have something that's preferred just because of galactic formation, but so many things happen to stars in their formation and reformation that I don't think the correlation would be as strong as what you would see in a planetary system.
I agree.
You agree? All right.
Yeah, just to make this clear.
I got it right.
Just to make this clear, I love having all these models handy. I have a model of our Milky Way galaxy. It's a spiral galaxy, and it's a disk. So if you're seeing it edge on, it looks like a line. And the question is, do all the planets orbit the stars in that same plane? And in our solar system, they don't. Although, when we look out on our solar system, we see all the planets going around as sort of on a line in the sky because we're in the disk of the solar system. We're seeing it edge on. And that line does seem to intersect the center of the galaxy. It's tilted at 60 degrees from the plane of our Milky Way galaxy. So our example of one already shows that the solar system does not line up with this galaxy. And these other planets, even though they're passing between us and their star, we don't know the actual tilt of these planetary systems. The planets might all be orbiting their star in this plane or in this plane. We'd still see them passing in front of their stars, just in different directions, which is very difficult to tell. But we don't know how that orients with the rest of the galaxy. We just know that if we don't see planets, it might be because they're orbiting in this plane, they're going around this way, and we never see them actually blocking the star. So our example of one already shows that that's probably not the case. It's possible that we'll be able to tell more about these things later, but it seems it's already clear that, yeah, it's probably not that well correlated with the galaxy.
Nancy, Mike Mentassa asked, wasn't this the first Earth-sized planet? Well, sorry, wasn't the first Earth-sized planet detected around a pulsar about 10 years ago? Do you recall that?
10 years ago.
It was longer than that. It was more than 10 years ago, wasn't it? It was like
92.
92,
yeah.
Right?
91 or 92, yeah.
From the
pulsar planets.
The pulsar planets, yeah.
Alex Wolfson, yeah.
Yeah.
Actually, one of those planets is, some people call it the first extrasolar dwarf planet, that some people think that they found something that is around the scale of Pluto. But the pulsar planets have always been considered kind of anomalies. Some people seem to forget to mention those planets and talk about planets around stars in the main sequence like our sun. So yes, that if you include those, you've got some pretty small planets in there.
Right, and planets are easier to discover around pulsars because pulsars have such a regular rotation rate that any anomalies, gravitational pull pulling them back and forth, you can tease that timing out of their, the Doppler shift as it's going back and forth. But
right.
Who would want to live around a pulsar?
Right, but those are basically burnt out cinders, and so if you're looking for something that can harbor life, those aren't the places to look.
Yeah. Phil, Andrew Spencer wants to know, what's the framed poster on the ground in your room?
Oh, that's a picture of Thunderbirds, the acrobatic team that flies the F-16s, and I flew with them a couple of years ago to film my TV show, and basically spent the rest of the day regretting it. Yeah, people always ask me, would you ever like to go out into space? And no, I get sick on swings in the backyard, playgrounds. Getting on the F-16 almost killed me.
I'll gladly take your place next time, Phil.
Yeah, have you gone on the vomit comet, Emily?
I have not, but I would be delighted to.
I would do it too.
Yeah, I get sick reading in cars. Yeah,
I'll take the invite.
No way.
Yeah. All right. Well, Emily, let me throw one back at you. Andrew Spencer asked as well. With that close to the star, they must be tidally locked. And so, do they know if that's the case? Are they tidally locked?
Hold on a second. With period. But I'm not trying to say period of time. With years that short, odds are very good that they're tidally locked. So that might make life very difficult for some of these places. You might have to live, only in the twilight locations on these planets, and the perpetual dawn and dusk that rings the planet. That might be the only place where you could have life. On the other hand, I think that we have to think outside of the box when it comes to life. Life certainly does that on Earth, and so there's lots more environments, I think, where life could exist than we give organisms credit for. One of the most interesting ones that I've heard recently is an article that somebody published about possible Titan-sized planets that are free-floating between stars in the galaxy, because probably a lot of these have gotten tossed out of their planetary systems as giant, much larger planets migrated inward and outward. And for certain Titan-like bodies with a thick enough atmosphere and an icy crust and potentially a liquid ocean, you could actually have life existing in small planets that didn't have any stars at all. So there's really a lot of possibilities out there for where life could exist that don't just require an Earth-sized planet in an Earth-position orbit around a yellow star.
And I think the more that people, I guess, as we start to discover liquid water in strange places here in our solar system, like on Europa or whatever it is that's going on in Enceladus, it just completely expands the concept of where life can survive and thrive as well. So we're both expanding the definition of where life can exist. And then if you include places that have nothing to do with with water, using other kinds of chemicals for its basic processes of life, that changes everything again. So there's both lots of places to discover them and a widening understanding of what it takes for life to survive. So lots more science to get done. Greg Lester notes, a bunch of my favorite space pundits holding an impromptu discussion about newly discovered exoplanets online. This is a geektastic convergence of some of my deepest childhood dreams realized. Same for us, Greg. This is awesome. And there's a bit of a confusion about how this Hangout works. Only the people that I invited can actually join the Hangout. Sorry, everybody. There's a maximum of 8 people in these Hangouts, and there's a few people that weren't able to show up. But in theory, the big problem that we had with the Hangouts we were doing before was that nobody could watch them. It was a sort of a secret meeting, I guess, where Big Astronomy gave us our marching orders. But now, everyone can be watching this, which is great. So then we can, if you want, and we have a way, I think, to be able to answer the questions. So.
And you're recording this, right?
And I'm recording this, right. So once this thing is done, the copy of this video gets dumped into my YouTube account, and then I can trim off the boring parts at the beginning and the end, and then post it back live on YouTube, or back onto YouTube, and then we can all embed it on our websites, and then it can remain forever. So I think this is sort of a neat way to get across this kind of conversation. So let's keep going with some questions. So, is it Bassam Islam wants to know, is it common for planets in another system to rotate around the star in the same two-dimensional plane? So, I guess that's what we have here in the solar system. Is it that same expectation that you're going to see that same configuration in other star systems? Anyone?
I always look to Emily. She's with the Planetary Society blog. That has the word planet.
Sounds good. Emily?
That's true. Yeah, it tends to be true that for all of the simulations that try to create planetary systems, you wind up with planets in the same plane. And there's a couple reasons for that. One is that all of the planets inherit their orbital motion from the initial spinning of the nebula that formed the star to begin with. So that imparts a particular direction and, a particular normal direction, an axis of rotation for everything in the system. The other thing is that when there is stuff that goes up above and below the plane, the inclinations are scattered. Some of them will go up over here, some of them will go up over there, and over time the ones that have the highest inclinations are the ones that are most likely to crash into stuff in the middle, and so as a result the inclinations tend to average out, and over time they all get closer and closer to that middle plane. It's only very far out at the edges of the solar system where collisions are much less energetic and where gravitational interactions with giant planets and things become more important, that you get a lot more scatter above and below the plane, like with the Kuiper Belt and the Oort cloud.
I've wondered about this because if you have planets that are that close together, like in this system, in the Kepler 20 system, where there are 5 planets orbiting the star inside of the distance of Mercury to the Sun, they're going to interact very strongly. Mercury, for example, is not tidally locked to the Sun. At least it doesn't orbit. It doesn't orbit one time for every one time it goes around, which is what you might expect. There are other they're called resonances. There are other resonances going on with Mercury. But when you have 5 planets stuck in there, they're all going to interact with each other. And if 2 of them actually wind up passing, if one of them actually is migrating faster than the other one, it passes it. And if there's even a slight tilt to this one versus this one might actually get that amplified a little bit. And I wonder, we're not really seeing the tilts of these planets, except I guess the transit times tell us if they're tilted or not. If one is going straight across the middle of the star and another one's going off near the top of the star, its transit time will be less. That would be interesting statistically to look at those and see just how well all of these planets are orbiting the star in the same plane. I don't know if that's actually doable or not, but I haven't heard anybody talking about that.
I think go ahead. You mentioned the resonances, and I'm betting that there should be some resonances involved if they're going to be in the stable orbit so tightly packed together. I haven't heard whether they found that to be the case, but orbital resonance usually allows planets like Neptune and Pluto to hang around together a little more easily than they otherwise would.
Well, we have those numbers. I guess we could just look at them. Sorry, go ahead, Emily.
Well, I think it's important to remember. Well, first of all, I don't think that any planetary solar system origin modeler would have predicted any of these kinds of systems before Kepler started detecting them. All of these things with gigantic planets orbiting really close to their suns, it's just not something that was on any of their radar screen to begin with until we started actually finding these. But the flip side of that coin is that the reason we see so many systems where there are so many planets orbiting so close to their suns is not because those are more common than our kind of solar system. It's just because those are the kinds of systems that are easy to detect by the transit method. If your planet is orbiting very close to a star, then it's going to be transiting that star much more frequently than, say, consider Earth, which only transits its star once a year. So as far as detectability goes, it's far easier to detect these things that have very short periods than it is to detect the longer period ones, and that's why they're just showing up so much more frequently in our statistics.
And if you think about it, in order to detect an Earth-like planet, you have to have at least 3 transits. They want to have 3 or more to be able to nail down the periodicity. And so you have to wait at least 3 years to be able to pick that up and confirm it.
Yeah, and also think about the fact that you're statistically more likely to see a planet that's on a slightly inclined orbit if it's closer to the sun, because the geometry works out that way.
Yeah.
Okay, so Nancy, I do have a question for you then. Jonathan Leggett asks, has SETI aimed their telescopes at any of these Kepler planets? So I guess the question is there any negotiations between the people discovering these planets and people looking for transmissions of intelligent civilizations?
Yeah, SETI is going to start focusing now on these Kepler planets, the Kepler area field of view that Kepler is looking for. So that should be pretty interesting. I don't know if they've started already, but I know that it's in the pipeline, that they're going to be starting to do that really soon.
That's really smart.
Yeah.
I mean, that really makes sense.
Yeah, that was just recently announced. So, again, I'm not sure if it's already started or if that's something that's coming up real soon.
Phil, do you know, Stephen Allen wants to know, what's the smallest planet that Kepler could see? Do you know what the sort of lower limit of this is, this method?
I don't know what the lower limit is, and that's a question that depends on a lot of things. The closer in a planet is to the star, the faster it goes around, and so the more often we see it transiting. So it can be smaller, but we get good statistics over time. So a big planet makes a big dip in the light. You can really see it. Smaller planets make they make smaller dips, and they're harder to see. But if you have more of them, you can build up better statistics. So there's a lot of stuff that's going on here. That also depends on how bright the star is. If the star is very faint, then it becomes difficult to detect any transit because you're already not getting very much light from the star. So if there's a little bit of a dip, you might not even see it. So I would guess that under the right conditions, these planets are probably about where you want to be looking. You want to be looking for a Mercury-sized planet would be interesting, but the goal here is to find an Earth-sized planet around a Sun-like star at the right distance. So I'm guessing that that's where they optimize their search, so that that's the kind of thing they can find best. But I'm guessing here. I am guessing.
Yeah, and I think with a lot of these kinds of instruments, one, the team gets a lot better at using their hardware and software, and so you find that they come up with these really clever methods to tease more data out of their technology, and so you usually find that they more and more impressive discoveries as the years go on. I remember was it the Mars, one of the Mars orbiters. They figured out a new clever trick to be able to tilt the spacecraft and take its images at an angle and then merge those with images they took a little later, and they were able to increase the resolution that they were seeing. Now that was blown away by the Mars Reconnaissance Orbiter, but for a little while they were able to get much better images that were going on. And I'll bet you, especially if Kepler gets maintained year after year after year, they're going to be able to tease more out of the equipment, and they're also, I think, going to be able to, they're just going to have more years worth of data, and that's always what you want, right? Is, what may not seem like a very big oscillation or, transit in the beginning, you look at it over 3 years, 5 years, 10 years, you can really start to pull together, more and more discoveries out of that data.
That's a good point, and I'll add to that two things. One is that the Kepler data is being saved, so it's going to sit in an archive. And if somebody 10 years from now says, I have this idea,
Yeah.
and they can apply it to that data, they may find, they may have some way of cleaning up that data and finding a lot more planets. This just happened with Hubble this year. There was an observation of a star back in 1998, I think it was, and they did not see planets around it. But at the time, we didn't have the software to analyze that as best we could. I actually worked on some of that data. 13 years later, they said, oh, you know what, we now do have this kind of software. They went back, looked at that image that was taken 13 years ago, fiddled with it, and boom, these planets popped right out of that data, and you can see them clearly. So, as long as you save the data, future techniques may be able to go back, archaeologically, you might say, dig through the data and find stuff that we didn't know was even there at the time.
Emily, what do you think this has an impact for the Drake equation? Tavis Settles asked this question. What about the Drake equation and this new discovery?
Well, of course, with the Drake equation, there's lots and lots and lots of unknowns, but it is very heartening to know that there are so many planetary systems out there. I think that it helps to at least increase the certainty that or likelihood that there's life out there. I don't know if it increases the likelihood that we will be able to discover any of it, or much less talk to any of it. But I think that knowing that there are so many more planetary systems out there is definitely a good thing for the question of, are we alone in the universe? That is, if you think it's a good thing that there are other aliens in the universe.
Hey, folks, I've got to ring off, but this
No
is
problem.
great. I wish I could stick around, but I'll look forward to seeing the recap. And so thanks so much for having me, Fraser, and great to see all you guys.
Thanks, Alan. And so if
Great,
people
yeah.
want to find more about Alan, he runs the Cosmic Log blog over at MSNBC and has been our mentor in the space journalism world for the last 10 years. So thanks a lot,
nice
Alan.
of
Thanks
you.
for thanks for joining us.
See ya.
And I'm going to have to take off too soon, actually.
All right. We can handle the drive-by.
Sorry about that.
science.
Next time I'll stick around for longer.
No, you know what? We put this together as a last-minute thing, and I sort of hatched the scheme about an hour and a half ago. So it's not surprising that people weren't necessarily able to make it. So hopefully next time we'll be able to give people more notice and more time and more promotion and whatever. As long as the quality's there. I mean, I hope that people are enjoying this. I mean, that's the goal. So if this is a nice way to get across this kind of science, I'm hoping that people will dig that.
So I'll say bye-bye, and thanks for the invite, and I'd like to do it again.
Thanks a lot. So
Yeah,
again,
Emily.
that was Emily Lakdawalla. She is she's at the Planetary Society. Good. Well, I think we're kind of out of questions. There's a few left, but I think we're sort of running late on time. We've been an hour so far, and I think we'll wrap it up here. Maybe stick around and answer a few questions in the comments. But thanks to Phil and Nancy and to everybody who participated in this. This was really cool, really fun, and I hope this helped everyone understand the discovery, give people some context, and a lot of really interesting stuff to talk about over the next couple of years. And I hope you guys all find this as exciting as we do. If you want to read more space and astronomy news and opinion, you can check out Phil Plait's website. Where do people find you, Phil?
Oh, I'm all over the web. If you go to badastronomy.com, that'll take you to my blog with Discover Magazine. I'm just Bad Astronomer on Twitter. I'm here on Google Plus, obviously. So it's just poke around, you'll find me.
And Nancy, we run Universe Today, so people can find out more mountains of space news on Universe Today, or follow our Twitter at Universe Today. Here on Google Plus, we're very active, and also Pamela. Pamela's like off on some exotic cruise. Dr. Pamela Gay, but she and I do Astronomy Cast, which is a weekly podcast about space and astronomy. And so if you kind of enjoy this casual conversation about spacey topics, you might enjoy that, which is at astronomycast.com. Well, thanks, guys. Thanks for joining us. All right, and we'll get this organized again if people enjoy it, or we'll never do it again if people hated it. All right.
That's great. Thanks.
All right.
Bye-bye.
Take care.